Hello, my name is Tançağatay Acar and today I'll be talking about conversion of context-free grammars to push-down automatons. As a prerequisite to this course, we need to know what context-free grammars are and the languages they recognize, which are context-free languages, and the automatons we use to produce these languages, which are push-down automatons. And if you remember, they are epsilon NFAs combined with a stack. So we know that context-free grammars and PDAs recognize the same language set, which are context-free languages. So there must be an algorithm to convert CFGs to PDAs and back, but this back part is not in the scope of this video. We only will investigate the conversion from grammars to PDAs. So if you remember what is a context-free grammar, it's a set of 4 elements. We have the non-terminal set, we have the terminal set, we have the start symbol, and we have some set of production rules. So the important thing about these production rules are we have a non-terminal character and we produce a set of terminal and non-terminal characters including the empty string. So this part will come in handy in the following slides. And if you remember what a PDA is, it's combined of 7 elements. We have the set of states, we have the alphabet, we have the stack symbols, we have the transition function that transitions on an input character, a current state, and the current top of the stack symbol, and it takes to the next state and a set of new stack symbols. So we need to have a way to convert these 4 elements into these 7 elements. So we need to find an algorithmic way to convert the CFGs to PDAs. To start, we consider only the leftmost derivations. So in leftmost derivations, we always use the productions of the leftmost non-terminal character to derive our string. So in algorithmic way, we actually do without thinking in our minds. We scan all of these forms from left to right, and what do is we always skip the terminal characters until we hit a non-terminal character, and we use one of its productions. Then at the next form, what do? We again scan from left to right. We skipped if it's a terminal, skip if it's a terminal. We stop at non-terminal, the first non-terminal that we encounter, then use one of its productions, and until we have string with only terminal characters. So how do we mimic this behavior with PDA? We use PDA's stack. So what do? We always start with start symbol. So we push the start symbol into the stack. Then in a loop, what do? We check if it's a non-terminal character, then it corresponds to the first non-terminal character that we encounter when we are going from left to right. What should we do? We pop this in stacks perspective, and then we push all of it, one of its possible productions. When we push, we have all of these symbols. Each of these characters, terminal and non-terminal, corresponds to a unique stack symbol. So we popped one symbol, we pushed 4 in this case. Now at the top of this stack we have the little a character, the terminal character a. So in a sense, the leftmost side corresponds to the top of the stack. Now what do? We check. If it's a terminal character, we should skip it. How do we skip it in stack? We pop it. But we shouldn't just pop it spontaneously. We should check if our input string also has this character. So what should we do? We should also check the input character. If it's the same with the terminal character at the top of the stack, then we pop it. Then when we encounter a non-terminal character, we again do the same thing. We pop it and we push one of its possible productions. So you might have some problems with this approach, like what if a non-terminal character has multiple productions? Then we take advantage of the non-deterministic behavior of the PDA. The popping and pushing of a production rule corresponds to a single transition in the NFA. But what we can do if we have multiple productions is we can have multiple transitions for the same non-terminal character, in which the non-deterministic automaton will take both transitions and explore all productions simultaneously for us. And when do we stop this algorithm? Well, when we have only terminal characters. And when do we have only terminal characters? What do? We pop all of them if the input is the same. So when we pop, we are left with the initial stack symbol, and when we do, we should stop and accept the string. So how do we structure such PDA? Well, we need 3 states. We have the start state, we have the loop state, and we have the final state. At the start state, we always push the start symbol into stack. This is always stays constant. And then what do? Well, we have the repetitive behavior. So for each terminal character in the CFG, we should have a transition that on that terminal character input, we should pop that terminal stack symbol if it's at the top of the stack. So we put all the corresponding transitions here, and then we should also have transitions corresponding to the non-terminal productions. So for each production rule, we should have that many transitions that are self-looping into this state. And at the end, we should have a transition corresponding to our stop condition, that if our stack is empty, we should accept the string, so go into our final state. Then we should formally represent this conversion. So for a CFG with the non-terminal and terminal sets and some set of production rules, there should be a PDA which has these exact 3 states all the time, and the terminal characters as its alphabet, and stack symbols corresponding to each terminal and non-terminal character, as well as initial stack symbol. And we should have these transitions that we discussed, and the start state is always the start state. The final states only consist of the final state, and we start with the initial stack symbol. If we do such things, then the language of the grammar should match with the language of PDA. So let's do an example. L is a language recognized by the CFG, which only has one symbol and has the binary alphabet. S goes to 0 as 1 and the empty string. So if you notice, the language this CFG describes is 0n, 1n, which has as many zeros as 1, and zeros comes first, 1s comes second. Now, we don't need to know this. We only need to have these information, but it's just nice to point out the language that we are describing. So what do? We don't touch the states. We always have this first transition, and we will always have this final transition. What do is we need to populate these transitions with corresponding elements. So how much how many terminal characters we have? We have 2 of them. So we should have 2 transitions corresponding to each terminal character. On the input of 0, if the top of the stack is 0, we the 0, and vice versa. And how many production rules we have? Well, we have 2. S goes to 0 S1, S goes to the empty string. Then what should we do? We should have 2 production rules there corresponding to each. We should have 2 transitions corresponding to each production rule. And this PDA recognizes the same language. Another example would be L is a language recognized by the CFG. We have 3 non-terminal characters, we have 3 terminal characters, and we have 5 production rules. So, can you recognize the language described by the CFG? Well, this is this language where we have as many B's as A's and C's. So the count of A's and C's combined gives you the count of B's, and they are in this order. So A's comes first, B's comes second, C's comes third. How do we construct our PDA? Well, we don't touch the states, we don't touch these transitions, we need to populate these areas. How many characters do we have? We have 3 terminal characters. Then we should have 3 transitions corresponding to each terminal character. How many production rules we have? We have 5 production rules. Then we should have 5 production rules corresponding to each. We should have 5 transitions corresponding to each production rule. So S goes to AC is implemented here. A goes to AB implemented here, and A goes to empty string implemented in here. And without thinking, without finding the language, without doing any efforts, in an algorithmic fashion, we can construct this PDA. Final remarks would be a CFG's ambiguity doesn't affect the method and the outcome. It just affects that for some strings you non-deterministically arrive to a final state simultaneously, but from different paths, taking different transitions in different order. But this does not affect the outcome. It still recognizes the same language. And the PDA constructed from the CFG is not unique to that grammar. You can construct different PDAs that recognizes the same language as that grammar, and so the CFG you can also implement rightmost derivations as well, but this is just one way of doing this procedure. Thank you for your attention.